Everyone. Today we're talking about an introduction to spectral graph theory. So for this talk, the central object that we're going to be talking about is the adjacency matrix of a graph. We'll denote this by A sub G or just by A whenever G is understood. And this matrix is a square matrix whose rows and columns are indexed by the vertices of your graph G, where we have the UV entry equal to 1 if UV is an edge in G, and UV equals 0 otherwise. So just this example to make sure we're all on the same page. If we look at the star, vertex 1 is adjacent to everything, so except itself. So in the first row, we put a 1 everywhere but the 0th entry. Similar to each of these guys is adjacent to 1, so we put 1 here, and we put 0s everywhere else because there's no other edges. And really, the adjacency matrix, the reason one would come up with it is just because it's a convenient way to store all the structure of the graph, whether you're edge or not edge. So just a nice, easy way to put it into a computer or to write it out without having to deal with embeddings in the graph. And the fact that it's also a matrix, some sort of linear operator, is just something that happens to come out of the way you're representing it, but it shouldn't affect the graph in any particular meaningful way. And the point of this talk is to convince you that this is not correct, and that in fact, somehow viewing A genuinely as a matrix and not just a convenient way to write out G can give you some extra power. And in particular, we're going to be looking at what the eigenvalues of our matrix tell us. And because the adjacency matrix is a real symmetric matrix, it has real eigenvalues which will denote by mu sub I and order like this. Okay. And kind of the first hint that you can do something with A as a matrix comes from walks. So a walk of length k in a graph is a sequence of not necessarily distinct vertices, which are sequentially adjacent to one another. And we'll say the walk is closed if you end up back where you started from. So in the picture, if this is our graph, then one walk of length 3 would be 1, 2, 3, 2. And a closed walk of length 5, for example, would be 1, 2, 3, 4, 1. Sorry, not closed walk of length 5. So that would be a closed walk of length 4. Yeah, and then if you want to do like 6, you do 5, 6. Those are closed walks. And it turns out that this information of how many closed walks or how many walks there are from U to V of some given length k is exactly the UVth entry of A to the kth power. And this will almost be just from definition. So we just use that A as a matrix and write out what this means. It's just the sum over here over the appropriate sequences of WIs. And because we're in an adjacency matrix, each of these terms will be 1 if and only if all the, like U is adjacent to W1 and W1 is adjacent to W2 and so on and so forth. In other words, if and only if it defines a walk. So it'll be 0 otherwise. So this is just exactly the stated lemma. All right, so we have this. And now a corollary of this is that the number of closed walks of length k is exactly the trace of A to the k. And this is because the trace of A to the k is exactly the sum of the UU entries of A to the k. And those are precisely the walks that start or correspond to walks which start at some vertex U and end up back where you started. In other words, it corresponds to closed walks. And you can write this in a bit more compact form as the sum of the eigenvalues to the kth power, which is convenient because now if you know the eigenvalues just at k, you can get this quantity without having to actually compute A to the kth power and then take its trace. And from this corollary, you can get a lot of other corollaries. So for example, I claim that from this you can derive that the sum of the eigenvalues to the second power is equal to twice the number of edges. So from this previous corollary, we see that I'm claiming that the number of closed walks of length 2 is exactly twice the number of edges. And this isn't too hard to see. So for any edge UV, you can define a closed walk by going U, V, U, or also V, U, V. So those are closed walks of length 2 where you just go forward on the edge and then back on the edge in either way. And it's not too hard to see these are the only ways you can get a closed walk because you have to, once you travel along one edge, you definitely have to travel back. So that shows this quantity here. And another fact, which I'll prove on the next slide, is that if a graph is bipartite, if and only if its spectrum, instead of its multi-set of eigenvalues, is symmetric about 0. So already we're starting to get some hints at what the adjacency matrix can do. It can tell you, or rather what its eigenvalues can tell you. It can tell you how many edges you have. It can detect whether you're bipartite or not. So we do generally get some information from these eigenvalues. But let me go now and prove this result here. So for one direction, we'll start with G, some bipartite graph with some explicit bipartition U sub V. And we'll let X be some non-zero eigenvector corresponding to the eigenvalue mu. Now to show that this multi-set is, to show that the spectrum of A is symmetric, at least as a set, we need to show that negative mu is an eigenvalue of A as well. And to do this, we'll construct some Y to have this eigenvalue. And namely, we'll do this by letting Y agree with X on big U, and on V, we'll have Y disagree with negative X, or with X, by setting it to be its negative. Now, if you look at A times Y, if you look at its youth coordinate, basically by the definition of the adjacency matrix and matrix multiplication, this is just the sum over all the YVs, which are adjacent to U. But each of these, because we're bipartite, each of these V's is in big V. So we know what YV is, it's negative XV. But now this sum over here is exactly the youth coordinate of A times X with a minus sign out. And we know X is an eigenvector. So this is exactly this quantity here. But now U is in big U, so that's what Y is. So we've shown that the youth coordinate of AY is negative mu YU. And the same argument works for V's. So we get that Y is generally an eigenvector of A with the correct, or the eigenvalue that we're looking for. And so this proof technically only proves that sigma A is symmetric as a set. But if you care a bit more, perform with a little more care, you can say that if you start with K of these X's, which are linearly independent and span the corresponding eigenspace of mu, then you can do this procedure on each of them and get back K linearly independent Y's, which correspond to negative mu. So you can say that the dimension of the eigenspace of mu is always at least that of negative mu, and vice versa by symmetry. So we get generally that. Okay, so that was one direction. So for the other direction, let's assume that A is the spectrum of A is symmetric about 0. Then one thing one can do is observe that if you sum over the eigenvalues to the kth power, this will be 0 whenever K is odd. And the reason is whenever you have a mu to the K here, you'll also have negative mu to the K, and those two terms will cancel. If K was even, this wouldn't work because then mu to the K and negative mu to the K would be the same value. They would be both positive. Summing over odd powers, we keep the signs and things cancel out perfectly. And if we recall, this quantity here counts the number of the number of walks of length K. So what this statement says is that G has no closed walks of any odd length. And in particular, this implies that G contains no odd cycles. If it did contain an odd cycle, then say if length K, then just walking along that cycle would also be a closed walk of odd length. So we conclude that G contains no odd cycles, which in particular means, which is equivalent to saying that G is bipartite. That proves that. And now I'm just going to very briefly mention a couple other results without proof. So one thing is that if you're a connected graph, then the number of distinct eigenvalues of your adjacency matrix is strictly larger than the diameter of your graph G. Another result concerns bounds on the chromatic number of a graph G. So we have this lower bound in terms of the largest eigenvalue mu1 and the smallest eigenvalue mu(n) due to Hoffman, and the upper bound due to Wilf. and this bound is typically a bit stronger than something called Brooks' theorem, if you're familiar with that. Another result due to Hoffman is that if you use a D-regular graph, then you can upper bound the independence number of a graph G by some scalar times n. So you can do a bit better than, say, it's at most n, which is the trivial bound. You can do it in terms of the spectrum. So this only works if G is D-regular. And we'll return to this near the end of the talk if there's time. And one last result I want to highlight and will actually prove is the following, which says that the largest eigenvalue, mu1, is controlled in some sense by the degrees of your graph. So it's always at most the maximum degree and always at least the average degree. And for proving the average degree, we're going to use basically this mini-max Courant-Fisher type result, which is that the largest eigenvalue mu1 graph, because A is a Hermitian matrix, it has the following forms: the maximum of this basically x transpose AX over x transpose X. And you can put in complex conjugates in general, but because we're a real matrix, we don't really need this. So for the lower bound, what you can do is take the all ones vector, and now again mu1 is exactly equal to this, and as a lower bound to this quantity, you can just plug in any x, in particular the all ones vector, and now I claim that you get this when you do this computation, namely this is basically the number of ones that appear in A, or really it's the sum of all its entry values, which will be exactly the sum of all the degrees if you look along each row. And then if you take 1 times 1, you'll get n there. And this is just by definition the average degree of a graph. And now it remains to prove this result. So to do this, we'll take some eigenvector x of A, which corresponds to mu1, and we'll let V be any coordinate such that the absolute value of xv is as large as possible. So then what we can do is we can write out A times x look at V's coordinate, and this by definition is mu1 xv. And this equality continues to hold if we take absolute values on both sides. And now this, by definition of matrix multiplication, is just the absolute value of the sum over all AUV times XU. The only terms that matter in this sum are when U is adjacent to V. So we can restrict our sum to that. And then we can do the triangle inequality to bring the absolute values into each of these terms. And now AUV is in general at most 1. And XU in absolute value is at most XV. Simply by how we chose V. So each of these terms is at most the absolute value of xv. So we get this. Because there are exactly the degree of V terms in the sum, each of which are at most xv in absolute value, we get this quantity here. And we can upper bound a degree of V by the maximum degree of the graph. So this gives this change in inequalities, and this gives that the absolute value of mu1 is at most the maximum degree, which in particular implies the stated result. And one can go through this proof of the upper bound and get a slightly stronger result, actually. Namely, if we take a graph G and M any Hermitian matrix, which in some sense represents the graph in the sense that whenever we have two adjacent vertices, its UV entry may not be 1, but in absolute value, it does equal 1, and for every other entry equals 0, then I claim that the largest eigenvalue of M is at most the maximum degree. And I can go through that proof right now. So up to this point, if we replace A's with M's, this is literally just the definition of matrix multiplication and what it means to be an eigenvector. And then when we made this transition, we said that, oh, we just throw away terms. The only non-zero terms of AUV are when U is adjacent to V, and that's still true by our definition of M, so we can get up to here with M. And now, to get from here to here, we said, oh, the maximum value, the absolute value of AUV is always at most 1. And here that's also true. The absolute value of MUV is at most 1. So we get here, and then this is just deterministic. So that proves this result there with the exact same proof. And I don't know about you all, but I don't personally like generalization for generalization's sake. So I mean, sure, one can prove this result, but there's no real reason to do it. At least one would think that. But it turns out this is not the case. So actually, this was a very key observation made by Hao Huang in proving something known as the sensitivity conjecture, which we'll now go and talk about. So let the sensitivity conjecture concerns the hypercube. So we'll define the n-dimensional hypercube in picture by its Q1 is a line, Q2 is a square, Q3 is a cube, and kind of geometrically this goes so on and so forth. But for us, we're concerned about matrices. So we can define this in kind of a weird way, more formally, in terms of its adjacency matrix. So we'll define the adjacency matrix of Q0 to be the 1 by 1 zero matrix. In other words, it's just an isolated vertex. And we'll define the adjacency matrix for Qn recursively by this formulation. And kind of the way you can think about this is for, say, example Q3, you build it by taking 2 copies of Q2, which corresponds to these matrices, A2 in this case, and then you add a matching between the matching vertices, which corresponds to these identity matrices put on the off diagonals. So that's how you define, one way you can define the adjacency matrix and hence Qn itself. And the other object or definition we'll need is that of an induced subgraph. So this is any graph that you can obtain from G by selecting some subset of its vertices and then looking at precisely the edges that involve 2 vertices of the subset. So for example, looking at Q2, here are basically all the induced subgraphs. For one, you could take as a subset all the vertices, which just gives you back the original graph. If you only look at these 3 vertices, you'll get this induced subgraph. If you look at 2 non-adjacent vertices, you'll get just 2 isolated vertices. You'll get 2 adjacent vertices. As your subset, you'll get this as your induced subgraph. And if you just pick a single vertex, you'll get just an isolated vertex. Okay. And the kind of the jumping off point for us is this result by Chung, Ferretti, Graham, and Seymour, which says if you take an induced subgraph of Qn on this many vertices, which is just half the vertices plus 1, then this induced subgraph has maximum degree at least roughly log of n. Right? And we can see this here. So we plug in n equals 2, what does this expression says? This says that if you look at any induced subgraph on 3 vertices, which up to isomorphism is just this guy, then it will have maximum degree at least 1/2. Or because things are discrete, it will end up being at least 1. And indeed, here we have maximum degree 2, which is certainly at least 1. And so a couple comments regarding this. The first is that this looking at half the vertices plus 1 is critical. If we only look at half the vertices, we can't get any sort of lower bound like this. And the reason is exactly this guy. So if we're only required to take half the vertices, you can choose it spread out enough so that they have no edges between them, and you can't prove any kind of non-trivial bound. But somehow, if you just get 1 extra vertex, suddenly you have to go from no edges and maximum degree, in particular 0, to having some vertex which has fairly large degree. But as we also saw, this bound is not sharp. In particular here, it only said you do at most 1, at least 1, but in fact you get at least 2. And you could ask, how well can you improve this bound? So in the original paper where they proved this, they also proved, in some sense, an upper bound. Namely, they found this cleverly constructed H on this many vertices, whose maximum degree isn't too big. So its maximum degree is roughly square root of n. So while log n is may not be the right answer here, you can't bump it up all the way to say n, for example. The best you could hope to prove is square root of n. And so they've posed the problem, and then people became really interested in this after a paper by Goffman and Lineal, and they proved that if you can show that if you can basically bump up this logarithm term to something like n to the epsilon for any fixed epsilon greater than 0, then doing this is equivalent to solving some important problem in computer science. And I will not get into the details on what exactly this problem is. It's called the sensitivity conjecture because of this, but we can talk about this at the end of the talk if there's time. Okay. So yeah, so that was, with this, people became a lot more interested in this, but it took 30 years by Huang last year to resolve this, and to resolve this in the best way possible in several ways. First of all, he improved this logarithm term to square root of n, which, as we saw was basically as good as one could hope to do. And moreover, he did this because it's a 30-year-old proof. You would think that the proof would be very long and hard, but in fact, it's very easy, and we'll prove it now in the next 15 minutes with everything we've learned. So the key object that we need to look at to prove this result is something that I'll call the twisted adjacency matrix of Qn, which we'll define in the following way. We'll let B0 be, again, the 1 by 1 0 matrix, and we'll recursively define Bn in this block format. If you just cover up this minus sign, you get exactly the definition of the adjacency matrix that I mentioned before. But now with this minus sign, you'll get almost the adjacency matrix, but now some of its entries are negative ones instead of ones. And the key property of this matrix is that its eigenvalues are fairly concentrated. In other words, they're only plus and minus square root of n, each with multiplicity half the total number of vertices. So in some sense, this is the reason why Huang chose to study this admittedly weird-looking matrix. If you look at the spectrum of the adjacent matrix of the hypercube, its eigenvalues are much more spread out. But this twisting operator of adding this minus sign somehow collapses all the eigenvalues under 2 points, which will be very useful to us, as we'll see in a moment. But now let's prove this. And to do this, we'll prove inductively that the square of these matrices is equal to n times the identity matrix. And the case n is 0 is trivial. And then inductively, we just look at the definition of Bn like this, and we just write out what it means to take its square. We'll get exactly this quantity here. And inductively, this is n minus I times the identity. This is n minus I times the identity. So working things out gives n times the identity matrix. Okay. And because of this, all the eigenvalues of Bn have to satisfy. If you replace Bn here with an x and I with just 1, you have to satisfy x squared equals n. In other words, all eigenvalues have to be plus or minus square root of n. And it's not too hard to see that the trace of Bn is going to be 0, and hence all both of its eigenvalues have to appear with the same multiplicity. Okay. And another kind of basic tool from linear algebra that we'll need is the Cauchy interlacing theorem, which says basically if you have some n by n matrix B and some, I should add the word real here, if you have a real symmetric matrix B and some principal submatrix C of B, then you can, roughly speaking, control the eigenvalues mu I of C by the eigenvalues of B. And don't worry too much about memorizing this. We'll just use the ones that I'll mention it on the next slide. Okay, so now somehow we have all our tools that we need to prove the sensitivity conjecture. So we'll start by picking some set of half the vertices plus 1 from the vertex set of Qn, and we'll let H be its corresponding induced subgraph. And now we'll let C be the principal submatrix of our twisted adjacency matrix, where we take all the rows and columns which correspond to this set V. And now by Cauchy interlacing, you look at what we get in this case. We get that the largest eigenvalue of C is at least the 2nth minus first largest eigenvalue of B. And we know exactly what this eigenvalue is. It's square root of n. And furthermore, if you look at the structure of C, we see that its UV entry is the same as the UV entry of B, which is plus or minus 1 if and only if U is adjacent to B in Qn, and hence also in H, and it equals 0 otherwise. In other words, C is some representative matrix of our induced subgraph H. And because of this, we saw by that generalization of our argument for the adjacency matrix that the maximum degree of H is at least the largest eigenvalue of C, which is square root of n, which is exactly what we wanted to prove. And I'll note that this step here, which was crucial for us, we just barely got by with this, right? If we had to go one further down eigenvalue, this would turn into a negative square root of n, and we'd get nothing. So really, this concentrating all these eigenvalues on these 2 points in exactly this format was very crucial to proving this result. Okay, so now that we've proven that, I want to talk about some limitations of the adjacency matrix. So we saw near the beginning of the talk that you can do a lot with the adjacency matrix. You can tell if you're bipartite, how many edges you have, a couple other things, but it's not perfect. You can't do everything. And the simplest example of it not being able to do everything is the following. So we have these 2 graphs, which are not isomorphic to each other, but they have the same spectrum of their adjacency matrix, -2, 0, 0, 0, 2. And such pairs where you have non-isomorphic graphs with the same spectrum are called co-spectral. And the issue is that as far as the adjacency matrix is concerned, or at least as far as the eigenvalues are concerned, these 2 matrices are the same. And that creates some complications. So for example, from this, we see that from the eigenvalues alone, it's impossible to determine whether a graph is connected, for example, because if the enemy gives you this multi-set of eigenvalues here, you'll have no idea whether he's talking about this matrix or this matrix. So there's no function you can take which takes its input these guys and outputs whether a graph is connected. And similarly, it can't tell, from this example, we know it can't tell whether you have a C4 or not, it can't tell whether it's a leaf or not, and so on and so forth. So finding these co-spectral pairs really helps show to what extent we can't do things with the adjacency matrix spectrum. But from the proof of the sensitivity conjecture, we see that we're not really restricted to only using the adjacency matrix. There we use this twisted adjacency matrix, which is what we need to solve our problem. And in general, you can just always try and pick your favorite matrix associated to your graph G and hope that this spectrum helps solve your problem. So somewhat more generally, at least the way I view it, spectral graph theory works in the following fashion. You start with a graph G, you then choose some matrix associated to it, you then compute its spectrum, and from this, you compute combinatorial properties of your graph G. And I'll note that all 3 of these arrows are important and non-trivial steps in trying to do things. So certainly, this step is probably the most important. If you have some matrix and its eigenvalues just tell you nothing about the combinatorial properties of your graph G, then there's no reason to even consider the matrix, because you can't do anything with it in the end. But equally as important is you need to be able to do these 2 steps. So as an example of this, you can consider the following matrix, x of G, which is defined to be the chromatic number of G times the identity matrix. And this matrix is very useful, or the eigenvalues of it are very useful. In particular, if you know the spectrum of this matrix, you know the chromatic number of your graph G exactly. So this arrow is great. The problem is these 2 arrows is, well, okay, you can define in principle this matrix xg, but you can't actually compute it. To compute this matrix in practice, you would have to compute the chromatic number of your graph G. which is quite hard. So this matrix is just not useful with regards to this theorem. And in principle, maybe you can cook this up in kind of a clever way where maybe the matrix is easy to compute, but maybe its spectrum isn't, at least in practice. That's why it's very crucial that the kind of matrix that you choose, you have some way of computing or at least bounding its spectrum, as well as deriving combinatorial properties of it. And there's various techniques one has, at least for kind of the standard matrices one uses in computing the spectrum, but we're not going to talk about that. Just know that the next two matrices that I talk about, there are good ways to computing this set, or at least, again, bounding it. Right, so I want to talk about two other common matrices used instead of the adjacency matrix. So the first of these is called Laplacian. So to find this, we first define capital D to be the diagonal matrices of degree of G. In other words, it's a diagonal matrix where the UU entry is equal to the uth degree, the degree of vertex U. And with this, we can define the Laplacian as D minus A. And as an example, we go back to this graph here. On the diagonal, we put the degrees of the matrix, and on the off diagonals, we put negative of the adjacency matrix that we saw at the beginning of the talk. And there are a couple different ways one might derive what this is. Certainly, when I first saw this definition, I was just very confused why one would ever consider it. So I believe the original motivation came about from spectral geometry of manifolds, where they have something called the Laplacian operator, and this is somehow an analog of that. Another way one might convince oneself that you can find it in nature is it arises as a certain boundary co-boundary operator. So if you view a graph as a one-dimensional simplicial complex, and you take the co-boundary operator from vertices and then the boundary operator from edges, this composition of the operators is the matrix you get associated to it. And another way you can view it is as a sort of chip firing operator in the abelian sand pile model. So in this model, we start off with all our vertices having some amount of dollars. And you can basically at each round activate a vertex. So if I activate this vertex here, what we'll do in this slightly modified version of the game is every vertex adjacent to it has to give it $1. So it ends up getting $4, and each of these ends up losing $1. Which you can represent as this row where it gains $4 and everyone else loses $8. And similarly, each of these other rows corresponds to activating a different vertex. So in the usual chip firing, you have these negative signs reversed, but in graph theory, this is typically how it's written. And there are various things that the spectrum of L can tell you about this thing here, though admittedly I don't know too much about it. In any case, going back to graph theory, we'll let lambda 1 through lambda n be the eigenvalues of L. And I'll note that if you look at the definition, it's not too hard to see that the all ones vector is always a null vector of L. And hence, the smallest eigenvalue of L is always going to equal to 0. And that'll be important in the statement of our next theorem, which is kind of the main thing you can do with the Laplacian matrix, and perhaps the most famous result concerning it. And it sort of the following. So we'll let tau of G denote the number of spanning trees of a graph G. Then it turns out that this, again, purely combinatorial property of your graph can be represented as basically the average value of the product of all the eigenvalues of L except the first one. So we started I equals 1. Sorry, we started I equals 2. And this is, of course, an important step because we just saw if we start at I equals 1, we'll get 0. But yeah, so this is a rather remarkable thing that somehow the eigenvalues of L can tell you exactly how many spanning trees your graph has. And again, I want to emphasize that this is definitely not the case for the adjacency matrix. The adjacency matrix couldn't tell whether you were even connected or not, let alone, so it couldn't even tell you if you have one spanning tree, let alone compute them exactly. But it turns out that the Laplacian is really built for doing this. And so let me do an example of this. So if you look at the definitions for the complete graph, one can check that the spectrum of its Laplacian is 0 with multiplicity 1 and n with multiplicity n minus 1. And if you plug that into this formula here, you'll end up getting that the number of spanning trees of Kn is n to the n minus 2. But note that spanning trees of Kn are exactly labeled trees on n vertices. So with this, we get something called Cayley's formula, which is that the number of labeled trees on n vertices is exactly n to the n minus 2. So this was originally proven by Cayley using more combinatorial arguments, but this matrix tree theorem is much more general and works for all graphs, which is very nice. So one other thing with regards to the Laplacian matrix is that if we have, this is developed by Gotzel and Newman, if we have an independent set S and we knew its average degree was T bar of S, then we can upper bound, then the size of S can't be too large. Namely, it can't be more than n times the scaling factor of 1 minus the average degree over the largest eigenvalue of Laplacian. And admittedly, in practice, I think this is probably not too easy to apply because typically you don't know the average degree of some arbitrary set. But there is one setting where you do know this, and that's if G is D regular. So if G is D regular, this D bar is exactly D because every vertex has degree D. And then this reduces to this formulation here. And I claim that this can be written, so these are the eigenvalues of the Laplacian matrix. I claim this can be written in this format using the eigenvalues of the adjacency matrix. And the reason for this is because when G is D regular, its diagonal matrix of degrees is just a scalar of the identity matrix. And hence L and A are related by this linear equation involving the identity matrix. And hence one can easily translate from the spectrum of L to the spectrum of A with some linear equation. And if you're very perceptive, you'll notice that this bound here is Hoffman's bound that I mentioned near the beginning of the talk. So this was a bound on the independence number of the graph in terms of the adjacency spectrum, which only worked when G was D regular. But with the Laplacian, it also holds here. It gives you the same result, but it also gives something stronger, namely it works even when the graph is not regular. And this is kind of a common phenomenon in spectral graph theory. So you'll often find that if you restrict yourselves only to looking at regular graphs, then it's often the case that there are many choices of matrices which will allow you to solve whatever problem you're interested in. Say, for example, bounding the independence number of a graph. So many things will work for D regular graphs, but it will often be the case that there's only one choice of your matrix, which is the correct one. Correct in the sense that it generalizes to non-regular graphs. So again, for the example of the independence number, if we restrict ourselves to D regular graphs, either Laplacian or the adjacency matrix will solve the problem for you, but it's only the Laplacian that generalizes in this nice way to general graphs. And the last matrix I want to talk about is something called the normalized Laplacian. So it's defined basically by starting with the Laplacian matrix and then scaling it down on the left and right by this diagonal matrix of degrees square rooted. And if you expand out the definition of L in terms of the adjacency matrix, one can also write this as the identity matrix minus the scaled down version of the adjacency matrix. And perhaps the most natural connection that's normalized, and as an example, we have the normalized Laplacian of this graph here. So we have ones along the diagonals and negative entries in the degrees and, in where there's edges. And each, the exact value of each entry depends on the degrees of both endpoints of the edge. Right, so the normalized Laplacian is intimately connected to something called random walks. So this process is defined by you pick some vertex to start on, and then each round at whatever vertex you're at, you uniformly at random pick one of its neighbors and then move over there, and then just keep repeating this process. So near the beginning of this process, if you only do it like 5 steps, then very likely you're going to be close to the vertex you started with. But if you do this a billion times, where the probability distribution of where you are is a bit much more spread out. And one can ask, how quickly does it take before you're quite spread out in some precise setting? So this is basically a Markov chain, and of use to people that do Markov chains is the probability transition matrix. And in this setting, this is the adjacent matrix times D inverse. And the reason you kind of see this is that on each vertex, the probability that you move to one of your neighbors is exactly 1 over the degree of the vertex, because you have that many choices to make, and you do so uniformly at random. So this is the matrix, and if we knew its eigenvalues, that could help us study this mixing time. But the problem is that this matrix is not symmetric, so it's not even obvious that it has real eigenvalues. But it turns out that this matrix is similar to a symmetric matrix, namely this guy, which you can get by multiplying by d to the minus 1/2 on the left and d to the 1/2 on the right. So because it's similar to this matrix, which is real symmetric, they have the same eigenvalues, and in particular, it has real eigenvalues. And you'll note that this matrix here is exactly this matrix here that shows up in the normalized Laplacian. So this was related to the normalized Laplacian by some linear combination of it and the identity matrix. And as such, the eigenvalues of normalized Laplacian are basically equivalent to the eigenvalues of your probability transition matrix. And because of this, it can be used to help control how quickly a random walk converges to the limiting distribution. And in principle, you could also define the normalized Laplacian just using this matrix without having to subtract I from it first. But it turns out that this exact formulation is often more useful for technical reasons. Namely, it has a very nice Rayleigh quotient form that you can work with. And yeah, that's the end of the talk.